Hi, my name is Greg Forrest, and this is the presentation for my final project at the Harvard University Extension School's Big Data Analytics course. The topic I chose is Apache Flume for collecting log data. My objective is to collect network traffic data and analyze this traffic for potential network intrusions. Primary technology is Apache Flume, which is a scalable and reliable system to collect data from many sources and pool into a centralized repository. Apache Flume is capable of collecting data from many different types of sources and also syncing to different types of destinations. Secondary technologies that I take a look at include Apache Hive, which provides SQL access to analyze the data stored in an HDFS directory. I also took a look at Apache Spark, in particular to generate a k-means model on top of the network data from MLlib, and use Spark streaming for pulling from a Flume source. The data set chosen is from the 1999 KDD Cup, which is kind of like a Kaggle competition before there was Kaggle. This data set contains nearly 5 million records of activity from a military network. Network attacks were simulated on this network, and that is the source for the data collection. Quick overview of Flume. Flume is a long-lived Java process. A Flume agent is comprised of three main components: sources, which is where the data is collected from; channels, store events generated from the sources, and then they ultimately sync to a sync process which receives the data from the channel and then writes it into its final destination. In the diagram below, we have a syslog source, flows over the channel to a sync that writes to HDFS. Some examples of the sources that you can use and configure from Flume include spool directory, so you can ingest log files from servers. Syslog is a protocol used by many network devices and Linux Unix systems. HTTP requests, JMS queues. You can even use other Flume agents as sources, and you can also use Twitter feeds as a source for Flume. Examples of sync destinations include HDFS, Hive, HBase, Kafka, among others. Some advanced data flows that you can set up with Flume include the following. So a fan-out approach is when you have one source, for instance in the diagram below, syslog, and then you build two channels which take from the source to two different syncs. One sync in this case for HDFS, another sync for a Kafka topic. You can also build agent tiers. So when you have, let's say, a bank of web servers that you're going to be collecting logs from. Another example of an advanced data flow with Flume is for scalability purposes. In the display below, we have three sources, each of them pulling syslog. Let's say those represent three separate routers. And then they're ultimately going to sync to a secondary tier Flume agent. The secondary tier Flume agent is going to collect all the events generated from the three sources and then pull those together and ultimately sync to an HDFS directory. Again, this is for when you have multiple web servers, routers, maybe the other devices that you need to collect data from. The Flume installation is fairly simple. You download the latest stable binary tarball from flume.apache.org, extract this tarball, set your environment variable for Flume home, and add the binaries to the path environment variable. For main configuration, one thing you would want to do is, if you go into the Flume home/conf directory, there's a template file. So set that template file, make a copy of it, and update the following line. Export Java ops is commented out. Uncomment that out, and you may also need to update some of those numbers on those two parameters, so -xms and then -xmx. These control memory allocated to the Flume agent. So in many cases I actually had to increase these numbers in order for my files to flow appropriately. In this next step, we're going to build a configuration file for our Flume agent. This Flume agent is going to have a fan-out approach where it's going to ultimately sync to HDFS and also an Avro sync for Spark streaming. Configuration files with Flume are hierarchical. They all start with the name of the agent, in this case final agent, and then you build upon those parameters. So for instance, in this first set of parameters, we're going to define the sources. In this case, Flume dir source 1 is the name of it. We'll define our two channels, and we'll define our two syncs. and then you build upon those parameters using the names. So for instance, final agent dot sources dot the name of our source dot channels. Here's where we configure the two channels that are going to be connecting into our source. Our source type is going to be a spool dir, so as files get copied into a directory, and the directory name is configured down here, Flume will be able to pick up those files coming in and generate events. One of the sync types is HDFS. In this case, we define HDFS, the directory that we're ultimately going to flow into. You can give the file a prefix name and it'll auto-generate some numbers based off of the timing. Give it a suffix. When it's in use, I chose underscore, which is a standard for MapReduce, to let systems know that the file is actually in flight. And then it's going to be a data stream, and then these two parameters here are something to play with. When I first did my initial data dump, I copied in the full gigabyte or so file, and it took forever to actually flow through Flume. What Flume was doing is it was rolling through records, and it was only taking about 7 or 8 records at a time to generate a 1K file size within HDFS. It just proved to be too timely. So if you increase those numbers, you can adjust the flow and the throughput from the Flume agent. So define the channel type to file, and then for the Avro sync we'll do the opposite. So just cut a couple highlights here. Just gonna ultimately sync to an Avro on the local host. I pick a port that's available, and then I set the memory type to, or the channel type to memory, so that we can quickly flow the events to the Spark streaming. To start the agent, you would issue this flume-ng command, give it the name of the agent, which in this case is final agent. You give it the name of the configuration file that you built, so which should be, if it's in the same directory it's fine, otherwise the fully qualified file name. A couple of notes for Spark streaming, especially when you're running it for Python. When you issue your Spark submit, you also have to pass in this packages parameter and point it to the Spark streaming for Flume, and then you give the name of your Python script. Some of the initial imports that you have to do from Spark streaming perspective, and to generate your first RDD. From PySpark, you'll want to import your Spark context as always. From Spark streaming, you'll want to do a streaming context, and then this is an additional one that we haven't seen yet. From PySpark streaming.flume, import Flume utils. And then you can define your Spark context as usual, and then also create a Flume streaming as down below. Once the data was synced into HDFS, what I did was I created a Hive table. This is actually an external table, so we're going to define the columns that we have, and then the file format. So this is where we have a row format. I'm going to use a Serde format, define it as a field delimiter of CSV, so with the comma, and then we're going to have say it's stored as a text import file. Ultimately, we're going to provide the location, which in this case was user gforrest/kddcup. So as we insert files into this directory in HDFS, Hive will allow us to query the contents of those files using the definition that we provide. For example, here's a Hive query. Just let's look at our output label and get a count of all the instances. So down we see our top 5 occurrences. One is this attack called Smurf, another one called Neptune, and then our third most common activity is just a normal network activity. Quick introduction to Spark MLlib for k-means. K-means is an unsupervised learning algorithm. This uses Euclidean distance in a multidimensional space. It's going to try to cluster your data into a predefined number of clusters. And then this is going to help us for anomaly detection. So in a multidimensional space, normal network traffic should show up, generally speaking, in the same cluster, and hopefully anomaly traffic will show up in different clusters. Some other interesting points: Spark MLlib also includes a streaming k-means algorithm. So as data streamed in through Spark streaming, you can actually update your k-means model. So for my use case, what I ended up doing was building a model off the data that we have available to us, save the model, and then ultimately what we can do is load this model back in and generate predictions on the test data coming in. Alright, here I'm pulling up this Python notebook I used to generate my k-means model. So up top we have our imports. Pretty typical. We're going to pull in our Spark context, and in addition I'm going to pull in a Hive context so I can pull the data out of the Hive table for the network data that we've already pulled into HDFS. So down here, using my Hive context, just a simple select star from the KDD cup table that we have defined earlier. Just take a quick look at the line count. We've got about 4.9 million. And then, since the data is pretty large and I only have a one node VM, I'm just going to sample about 20% of the data. So first thing, just take the RDD, give it an index, do a sample of about 20%, and then pull that index back out. Next step is I'll pull out the features. So k-means needs to be all numeric features, so I'm going to pull out the numeric ones. The text labels didn't really have significant value, so we'll ignore those for now. So once I pull out all the features, I'll also pull out the labels just into a separate RDD. Just as an example, here's what the data looks like. So next step. So k-means is something that's really susceptible to features that have a high variance. So what I'm actually going to do is from the MLlib, I'm going to try to pull out the standard scaler and see what that can do for us. So the standard scaler, what we're going to do is we're going to actually take the data, normalize it, scale it down, so you fit a model. So we'll use our KDD features, and then we'll ultimately transform the KDD features with our model. So I'm going to cache this just so we have in memory for the next set of steps. So from pyspark.mllib.clustering, I'm going to import the k-means. So I'll take a quick look, just a simple cluster of two, generate a model. So first thing first, we're going to build the clusters with k-means.train, pass in our features that have been standardized, and then k equals 2, so we're going to have two clusters. And then max iterations is something that you want to run as many times as possible to make sure that your model converges. And then initialization mode set to random. So I'll define a function just so we can generate some errors based off our predictions and actually return. So this is going to be a within set sum of square error metric, and we will use this going forward to estimate how well a model actually performs and try to pick a better value of k. So here we see the printout from the result of k equals 1 through 9. We can see that the sum of squared errors is decreasing. Now let's just try to plot it out so that we can actually treat it and see if we can find an elbow with our data. So picture right here. So as we can see, we decrease rapidly from k equals 1 down to k equals 4, and then the decrease within sum of squared error decreases, and it's decreasing, but the rate is not like it was from k equals 1 to k equals 4. So k equals 4 is what we'll use to generate our final model. So we'll come back to the Python notebook. So we'll generate a final model using k equals 4, and then we'll actually do some predictions off of that, and then we'll ultimately zip that back in with our labels data set so that we can actually see the results. So here we see we have normal, and we have a cluster representation of 1. And we'll do some more analysis. So I'll load this into Spark SQL, just run a couple queries. So for the most part, we see that the labels fall within a single cluster. In this case for Neptune, which was one of our top offenders, more data falls into cluster 3 than any of the other clusters. Unfortunately, some do fall into, in this case 2, fall into cluster 1, which our normal activity also fell into. So one other thing we can do is, again, let's just do a final summary of our top 5 offenders. So we see the Smurf attack falls into cluster 2, Satan falls into cluster 0, and Neptune falls into cluster 3, where our normal traffic falls into cluster 1. IP sweep is probably something we'd want to be worried about, which also falls in the same cluster as normal, but regardless, that's where we stand. So we actually have a pretty decent model that we can use to load up and predict on our incoming data from additional network traffic. So in summary, Flume worked as advertised. There was a little bit of tweaking just so that I could get the data throughput somewhere acceptable, but that didn't take much of an effort. The Spark MLlib k-means clustering. We didn't have a high 90% accuracy rate, but it was definitely a good start to start flagging traffic as either normal or abnormal. Hive for ad hoc analysis. That's great for companies with a lot of people with SQL experience. So just in general, to wrap it up, this is definitely something I would implement in a professional environment. It appears to be scalable and reliable and redundant. So it's great technology. There's many sources that you can pull from out of the box with Flume. And then, as we saw with other tools within the Hadoop ecosystem like Spark, you can provide some great tools on top of it. Thank you for watching my video. If you have any questions, feel free to comment. Thanks a lot.